Video, what we're going to do is we're going to differentiate y equals sine x. Obviously we know the answer is going to be cos x because we've done that in the past, but we're going to do it from first principles. On the WJC specifically mentioned are sine x and cos x that you need to be able to differentiate from first principles. You are not expected to be able to differentiate tan x from first principles. So let's just deal in this video with sine x. Right, well, there's a number of things you've got to remember. First of all, from year 12, you've got to know this, which is the basic expression we're going to use to work out dy by dx for any given function y equals f of x. Now, in this particular case, we're talking about the function y equals sine of x. So f of x in this question is going to be sine x. So the first step is dy by dx will be the limit as delta x tends to 0 of, and instead of f of x plus delta x, we're going to have sine of x plus delta x. Take away, instead of f of x, the function we're dealing with is just sine x all over delta x. So that's the first step. You get a mark for doing that. This will be equal to, okay, for the moment, leave this alone, limit delta x tends to 0 of, and now a bit of trigonometry work that you should already be aware of. We're going to apply the compound angle identity that you should be aware of from your trigonometry work to this expression here. Now you should know from your compound angle work that the sine of a plus b, whatever a and b are, here a is x and b is delta x, but the sine of a plus b, you should remember the identity from trigonometry work is the sine of a, the cos of b, plus the cos of a multiplied by the sine of b. And that there is something you need to know, and we're going to apply it for the next step in this proof. Okay, so here we go then. So what does this mean? Limit delta x tends to 0 of the sine of x plus delta x. Applying this will be the sine of the first, cos of the second, sine of x, cos of delta x, plus cos of the first, sine of the second, cos of x, sine of delta x. So that there is the same as that there. Take away sine x, that's still there, all divided by delta x. Okay, now the next bit hinges on the fact that at the end, ultimately, we're going to let delta x shrink to nothing. If you remember where the proof from first principles is derived from, we have this delta x notation tending towards nothing. So that means that delta x is going to become very, very, very small, ultimately shrinks to nothing. Now, another thing that you should be aware of from your trigonometry work is that if theta, or the angle x, delta x, whatever it is measured in radians, and we're going to be using radians in any calculus involving trigonometry, as I've mentioned in previous videos. For any situation where we have radians, that if the angles are very small, okay, so for small angles, I'll just write this so you can see this. For small angles, let me remind you that the sine of theta is exactly the same size as theta, provided these are measured in radians. So theta in radians is the same as sine theta in radians, provided the angle is very small. Also, you need to be aware that the cos of any angle, theta, this is a general theta I'm talking about, the cos of any general angle theta in radians is approximately the same as 1 minus theta squared over 2, provided, again, we're measured in radians and the angles are very small. Now, ultimately, the delta x, which is what I'm going to deal with here and here, which is now an angle, delta x is going to shrink to nothing. So this cos delta x and this sine delta x will have angles in rads, because we're dealing with rads, plus they're going to shrink to nothing, so they're going to become extremely small. So I can apply these two facts to those two particular terms there. So what we're going to do is say this, lim delta x tend to 0, let me just move it up slightly, lim delta x tend to 0 of, now I'm going to say sine x stays the same, cos delta x now, cos delta x, well from this, cos of an angle is the same as 1 minus theta squared over 2. So it's 1 minus not delta x is going to be delta x in a bracket squared over 2. So instead of 1 minus theta squared over 2, if it's cos theta, if it's cos delta x, it's 1 minus delta x squared all over 2. So that and that have been dealt with, plus, now it's cos x times the sine of delta x, and the sine of delta x, well, sine of an angle is the same as the angle itself provided theta is in rads and the angles are small. Because delta x is tending to 0, then delta x is going to be small, or tending to 0 in fact. So we can change the sine of delta x simply into delta x. Sine of theta is the same as theta, sine of delta x is the same as delta x. Minus sine of x, still there, don't forget that, all over delta x. So I've replaced the cos delta x with that and the sine delta x with that, purely because we are going to be saying that delta x shrinks to nothing, so delta x is in effect very small, so you're allowed to do that. Okay, now I'm going to expand out this bracket, so let me just lift this a bit. So it's lim delta x tends to 0. I'm going to expand this out, so you're going to sine x times 1 is sine x, minus sine x times this is going to be that, plus I'll leave this one alone, and don't forget I've still got the minus sine x on the end, I'll just squeeze that in there, all divided by delta x ultimately. Now you'll notice that you've got a sine x and minus sine x, beginning and end, they can cancel out, so they vanish with each other on the top line, and we end up with lim delta x tends to 0 of, and what we're going to do now is simply take this top line here and divide it by the delta x. So remember, this is sine x multiplied by this thing squared over 2. So if I divide this by delta x top and bottom, you're going to get minus sine of x, and then it's multiplied by delta x over 2. The square cancels with that. Plus, then the cos of x delta x cancels with the delta x. So you just get cos of x, and everything else is gone. So we get to there. And now finally we say, to get the final answer, we say, okay, we have applied the principle that delta x is shrinking to 0 already to get these two expressions, but we're going to apply it in full now by saying, delta x tends to 0, so any delta x is in here now shrink to nothing, so that becomes nothing there. So if I apply this, we end up with we're applying that, so now it vanishes from the expression I write down. That becomes nothing, so you end up with minus sine of x times nothing plus the cos of x. And of course minus sine of x times nothing is just nothing, and you just end up with the answer cos of x. And of course you should know that when you differentiate sine x, you end up with cos x. And so there you go. There is the proof from first principles for y equals sine x. It involves three basic ideas. It involves the basic expression you use for first principle differentiation. It involves the sine of a plus b compound angle identity. And it also involves small angle use where these expressions are equivalent for radians. And there you go. That is how you differentiate y equals sine x from first principles.